So I'm just writing this down. I'll just call it recap. And it is going to be just in the OneNote, but really it's just a matter of you paying attention here. So just very quickly, when we started off the idea of trig, we started off the situation where you have these triangles that are similar. And so based on a reference angle, which we might call theta, that angle will always be the same for the same ratio. Now we learnt about 3 set ratios. So the first one was sine, and that was based on the opposite side over the hypotenuse. So remember SOHCAHTOA, that acronym. Tell me, next one, cos is adjacent over hypotenuse, and the last one, tan. Someone different? Opposite over adjacent. So what that means is if I have a triangle, and if I know that this side is, 10 and this side is 12, then if I have that same ratio where this side might be 30, which means that side would be 36, they are similar triangles because the two angles are the same, and two sides, well, by default, because it's a right triangle, it's actually what condition here? You've got your right angle, you've got the hypotenuse, and you've got a side that are in the same ratio. So by RHS, those, without even knowing what theta is, those two triangles are similar. Or I guess we could use theta and the right angle, because I've said they were the same angle, and use AAA as the condition that they're similar. Regardless, what I'm trying to say is that angle theta will be the same for both triangles because they are similar. The scale factor here is 3. So if I know that, for example, this one, because it's opposite and hypotenuse, although we could find that third side using Pythagoras, but we won't go there. If I know that sine theta is 10 on 12, then that ratio, that angle theta, will still be the same for the 30 on 36 because of that same scale factor. And so if I give you, so this is how we kind of started, and then if I give you a question where, well, let's say this side, if I know this side is 20, same angle theta, what must that side be? What's that side got to be? Just using a bit of logic. 24. Why does this have to be 24? Yeah, the scale factor is 2. So each side, the triangles are similar. Side 10 doubles to 20. So side 12 has to double to 24. So depending on the ratio, whether you have the opposite hypotenuse, whether you have the opposite side adjacent, whichever ratio it is that we've got, there is consistency because they are similar triangles. And so if those ratios are the same, the angles will always be the same. And so then last lesson, we looked at the idea of finding side length. So if I know, let's say that this angle is 23 degrees and this side might be 15, I can find x. How do I find x? What do I need to do? So is it cos? So let's think about it. Opposite the angle under consideration is x. So that is the opposite side. What does the 15 represent? Hypotenuse. So you've got opposite hypotenuse, so we should be using sine. So the sine of the angle is opposite over hypotenuse. So sine 23 degrees equals x on 15. And therefore x will be 15. Undo that, divide 15. At this point now, we are solving an equation. Undo the divide 15 by timesing 15, and whatever that is, we can all use our calculator to figure that value for x out. Next question, next type of question, very similar idea. This time, we might as well stick with the same angle. But this time, I'm going to say, well, what's this side? And I don't know, we can stick with 15 if we like. That side's 15. How do I determine y based on that information? What ratio am I using? cos. Right, why is it cos? Adjacent on hypotenuse. So same deal. It's cos because cos 23 is y on 15. So y is equal to 5 times cos 23. And if we've done this right, because I've used the same triangle and exactly the same measurements actually, if I use Pythagoras now, once I work out x, I can actually use Pythagoras to find y, or use cos in this way to find y. That should give me the same answer. If you don't believe me, you can try it, but not right now. And then I'm going to use a completely different triangle now. The other type of problem that we did, let's say that's 15 degrees. And I don't know, this is 8 centimetres and this is K. What's different about this one apart from the ratio? Firstly, tell me what the ratio is. Oh. I've given you a big hint, haven't I? With the T there. Why is it tan? You don't have the hypotenuse. You've got the opposite and you've got the adjacent side. So tan theta, opposite over adjacent. So tan of the angle 15 equals 8 on K. So apart from the fact that this is tan, what's different about this one compared to those other two? Yeah, we don't have the hypotenuse. Where's the variable placed? In the denominator. So because in the denominator, the solving is a little bit trickier. So we have to undo that divide K. Once you get the hang of these, when we practice them, we can go straight to this step and say, well, tan K must be 8 divided by tan 15. But I'm going to just remind you of the reasons why we can do that. So undo that divide K by multiplying both sides by K. So that leaves you with K times tan 15 degrees equaling 8. And then we undo the times 15 by dividing both sides by tan 15. Sorry, not times 15, times tan 15. So that's why. But you don't need to do that every time. Once you get the hang of these, you should recognise that when the variable's in the denominator, we are dividing by that trig bit. If it's in the numerator, that's an easy one to show because of that undoing divide 15 with times by 15. It makes sense. And that's kind of where we left off last time I saw you. So that idea of similarity, we've got these three ratios because they work always, because the triangles are always similar every time we set up a ratio like this. So again, with this one, I just want to reiterate, because that's really important. I'm going to figure out tan 15 here, 8 divided by tan 15. 29.86 will do. Sorry, not angle, centimetres. So just want to reiterate, if I have a triangle, again, if that angle is 15, if that side 8 is not 8 but 16, you should be able to tell me what K is based on what we just calculated. K's got to be what? It's got to be double. Are you girls listening at the back? So it's got to be double. So it's got to be nearly 60, right? Whatever 29.86 times 2 is. Whoops. Because this is double. And so the side lengths for similar triangles are double. They're similar because the angles are the same. So it's really important to understand that idea, not just calculate your numbers and spit out an answer that people can do. I mean, even course 2 do these questions, right? But you've really got to understand why they work, because this trig stuff is the basis behind, you know, trig stuff that you do, and then we link trig to graphs as well. So you've done quadratic graphs, we've done reciprocal graphs, we've done linear graphs. There's also trig graphs. Really interesting. Won't be this year, but trig graphs are that's the ones that it's like wave motion. For example, alternating current, direct current, I don't know, somewhere linking there with physics as well. But all your trig graphs also link nicely to the triangles, which link to this thing called the unit circle, which you'll learn all about next year. So what I want you to look at now, though, what we're going to focus on today is we've done questions where we're finding side lengths. Now we're going to do some questions where we're finding angles, just to show you how that works.